So I think we have a couple of minutes to go through an example. I like to draw on my little app. So this is supposed to be an egg in a microwave. I don't know. It's an egg in a microwave. So let's believe that it's an egg in a microwave and then try to model it. So what I want to do is look at this example where we have generation occurring. Right? A microwave is basically like you're irradiating this thing, and it's volumetrically absorbing that radiation and converting it into heat. So it's doing that in a way that actually, you might notice like if you microwave something and it's still cold in the middle but burning hot on the outside. That's because that generation is a function of radius. Right? That absorption is a function of radius. So let's assume it's some simple model where we say the amount that I'm generating or converting into heat is just the radius times some constant, some coefficient. So as I get out to the outer edge, that's the highest amount of generation. As I get to the inner core, it's basically zero. Right? So we're going to take this non-uniform generation and just go through the example doing it in cylindrical coordinates. Okay, we'll maybe get halfway through this. So let's start with our control volume. I've sketched that in the bottom left. So at radius r, you have q dot r coming in. This is now dr, this width here. So leaving, we have q dot at r plus dr. And internally, we have g dot triple prime, which is a function of r times d volume. Right? This is a v, d volume. Okay, so we'll kind of go through the steps so you see what happens. So we'll take the energy balance. This is now q dot r minus q dot r plus dr plus g dot triple prime as a function of r times dv is equal to 0. I'm going to expand this term out, and we get q dot r minus the quantity q dot r plus dq dot r dr dr plus, now let's substitute in our expression for generation, and that is just r times alpha, now times the differential volume. So the differential volume, my egg is a sphere, just a weird egg. So it's a sphere, so we need some differential spherical volume. So it's going to be 4 pi r squared times the differential width, which is dr. That all equals 0. All right? So r alpha is the generation, 4 pi r squared dr is my differential shell, like it's a spherical shell. Okay, so simplifying that down, we get dq dot dr is equal to r times alpha times 4 pi r squared. All right, so then we have our governing differential equation in heat. We need to substitute in the rate equation, right, Fourier's law, in spherical coordinates. So in spherical coordinates, we say q dot is equal to minus k times 4 pi r squared dt dr. Right, that's just Fourier's law. So sub that in, and we get this. We get d dr of the rate equation minus k 4 pi r squared dt dr is equal to r times alpha times 4 pi r squared. Okay, so we can cancel out this 4 pi. That goes away. We can divide through by minus k, but we can't divide through by inside the argument on the left, right? That r squared can't come out because it's the independent variable. So we're left with, sorry, where are we going here? So we're left with this equation. We have dr r squared dt dr is equal to minus alpha over k times r cubed. okay? Governing differential in temperature, but you'll see now, not only is it a non-zero term on the right, this is not equal to 0, there's stuff on the right-hand side, but the independent variable is also on the right-hand side, right? So it makes it even a little bit more complicated to solve. Fortunately, in this case, it's still separable, right? You can bring that first dr over to the right and integrate, and then go from there. So let's keep going. Let's just get to that point. So I'm going to write that here. So it's separable. I guess we'll skip the steps of integration just so I don't have to write it in the last minute. But you integrate the left side, so you get r squared dt dr, and then the right-hand side you get, minus alpha over k times r to the 4th divided by 4. Right, and then you divide through by r squared. You drop that r quartic term down to r squared, and then you can integrate again. So okay, you end up with this solution, which is t is equal to minus alpha over 12 times k times r cubed minus c1 over r plus c2, right? So that's the temperature solution. Okay, that's far enough for today. We'll maybe finish this up on the boundary conditions next time. Thanks.